Good day. The discussion will focus on the review of the concepts of geotechnical engineering. First, soil as a multi-phase system and is composed of the following. First is the soil solids. This is the solid particles of the sample soil. Second is the void or the space section. It is the space between the solid particles that is either liquid, that is water, or gas, that is air. The different conditions are, first, the dry soil, which is with no water in the void space or air only. Second is the moist soil, that is, void space is partially filled with water. And third is the saturated soil. So void space is filled with water, therefore there is no air. So the parameters for unit weight determination are, first, the specific gravity of soil solids or G sub S, wherein it is the ratio of the soil solids unit weight to the reference substance unit weight, which is water, or that's Gs equal to gamma S all over gamma of water. Second is the moisture content or water content, or symbolized as small letter W. So it is the ratio of the weight of water to the weight of soil solids, or that is W equal to W sub W over W sub S. And it is either in percentage or decimal form. Third is the void ratio, or small letter E. It is the ratio of the volume of voids over the volume of soil solids, or V sub V over V sub S. And finally, we have the degree of saturation, or capital S, wherein it is the ratio of the volume of water to the volume of voids, or that is V sub W all over V sub V, and it is either in percentage or decimal form. So for the relationship of the four parameters, we have now the GS, W equal to ES, or that is GWES. So the relationship of the parameters and unit weight, on the other hand, can be expressed by the aid of the block diagram. So for the unit weight, the value of gamma is the total weight over the total volume. The dry unit weight, or gamma sub D, is the weight of soil solids over the total volume. Again, for dry soil, the weight of water is 0 and the weight of air is negligible. Thus, by block diagram, we have now W sub S, or the weight of soil solids, as the GS gamma W, and for the total volume as 1 plus E. Thus, our equation will be gamma dry equal to GS gamma W all over 1 plus E. So for the moist or saturated unit weight, depending on the condition of the soil, so we have gamma M or gamma sat. It is equal to the combined weight of soil and water over the total volume. Again, for the weight of air, it is negligible. So for the first possible equation, we have W sub S equal to GS gamma W, while W sub W, it may be GS W gamma W. Then, for the total volume, still it is 1 plus E. On the other hand, other possible equation is, we have W sub S again, GS gamma W, while for WW, it is E capital times capital S times gamma of water. And again, our total volume is 1 plus E. Note, consider only the block diagram if parameters are provided. For saturated unit weight, use S equal to 1. And for our moisture content, for W, and the degree of saturation, that is capital S, values are in decimal form. Again, W and S must be in decimal form. Next is the review of total stress, or sigma. It is the representation and estimation of the total weight of the soil column. It includes all the components such as weight of soil solids and water. And note that weight of air is negligible. In equation, we have the sigma equal to the sum of the unit weight of the soil. For this gamma, it is either dry, moist, or saturated. Then multiply that with the corresponding depth of that strata or layer, where gamma is equal to the unit weight of the material, and h is again the height or depth of the material or the soil. The total stress therefore for point A along the section A to A is equal to the gamma of water times h, or that is the height above this sample soil, then plus, so we have now below h, the capital H, we have the gamma of that saturated soil, then multiply it to HA, so which is the total depth, then minus that corresponding height of water above the soil. So, what are the components of the total stress? So again, the total stress is equal to the U plus the sigma prime. And what do this symbol represents? First is the letter U, or the water in the void space, otherwise called as the hydrostatic pressure, or water pressure, or the neutral stress. In equation, it is equal to the unit weight of water or gamma water times the respective height of that liquid or water. The second component is the sigma prime, or the soil solids at their points of contact, otherwise known as the effective vertical stress. So from the original equation of total stress, if we will now modify it, we have the effective stress is the total minus the pore water pressure, or that is the sigma minus U. In relation to the effective stress, we have the effective soil unit weight, or the gamma prime, or known as the submerged unit weight. In equation, we have gamma prime equal to gamma sat, or the saturated unit weight, minus gamma W, or the unit weight of water. And if we will identify directly the value of the effective vertical stress, it may be estimated as the sum of the product of the effective unit weight identified above and the corresponding soil depth. So for the notes, the stress acting for a certain point is the weight above it. So the total weight above it. So for layers of soil, apply sum of stresses from free surface until this sample point or the required point. And for dry soil, consider effective unit weight as equal to the dry unit weight. Next, we have the review of the shear strength of soil, defined as the internal resistance per unit area that the soil mass can offer to resist failure and sliding along any plane inside it. So for the purpose, the strength parameters will be used to analyze soil stability problems related to, first, lateral earth pressure on earth retaining structures, second, the bearing capacity, and last is the slope stability. So for the condition, soils generally fail in shear. At failure, shear stress along the failure surface reaches the shear strength. And the soil grains slide over each other along the failure surface. So therefore, there is no crushing of grains. And finally, at failure, the shear stress or tau along the failure surface reaches the shear strength that is tau sub F. So due to the application of increasing normal stress on a sample element, the value of shear obtained may be used to plot this more column failure criteria. So as shown. So this line represents the critical value, which therefore serves as the boundary between the safe zone, so below that curve, An example is our point A, and boundary of the failure zone, so which is above that line, an example is point C. And for our critical point or critical zone, we have now point B. So again, the total stress is we have tau sub F equal to C plus sigma times tangent of P. While for the effective stress, we will then convert our C to and P to prime or C prime, as well as our stress, we have now our sigma prime. And for our angle, we have now P prime. So where C is the cohesion, P is the angle of internal friction, sigma is the normal stress on the failure plane, tau sub F is the shear strength, while C prime and P prime are the parameters based on the effective stress. And please do take note again that parameters C and P measures are the measures of the shear strength, and the higher the values, the higher the shear strength. But again, if we will have a review, so for a certain soils or components of soil, such as for sandy soil, for the value of our C, it is approximately equal to 0. So we have only a value of P. So please do take note of that. Again, for sandy soil, we will consider it as cohesionless soil, or C is equal to 0. So the following are the laboratory tests for the determination of shear strength parameters. So again, our C and P. So we have now the direct shear test, the triaxial test, the direct simple shear test, the plane strain triaxial test, and the torsional ring shear test. Now let us define the drained and undrained condition. For the drained, so the changes in loads are slow enough or remain in place long enough so that water is able to flow in or out of the soil, permitting the soil to reach a state of equilibrium with regard to water flow. The pore water pressure are controlled and are unaffected by the changes in loads. So a sample of the test in which a drain will be considered is a direct shear test. On the other hand, so for the undrained, so the changes in loads occur more rapidly than water can flow in or out of the soil. And unlike for the drain, so we are dealing with the tendency that the water can move out or move in the soil because it is slow enough. Next, for the undrained, the pore water pressure, so there will be an increase or decrease in the voids in response to the changes of loads. So again, since the water cannot flow in or out due to this rapid application of loading, so there will be an increase or decrease right away of the pore water pressure, or our small letter D. So a sample of the test for this undrained condition is the triaxial test. So next is for the disturbed and the undisturbed samples. So for the disturbed sample, it is the samples in which the natural structure of the soil got disturbed either partly or fully during sampling. So we have the non-representative sample, which consists of mixture of materials from various soil or rock strata, or are samples from which some mineral constituents have been lost or got mixed up. These are suitable only for providing qualitative information such as major changes in subsurface strata. Example, we have now soil sample from auger and washed boring. While the representative sample, so for this one, the constituent minerals are retained, but only the structure of the soil got disturbed. There are changes in water content, and it is used in the determination of physical properties like Atterberg limits and specific gravity. On the other hand, for the undisturbed sample, samples which are subjected to minimum disturbances. purely undisturbed sample is an ideal condition because all samples, even using precise equipment, get disturbed. So the samples are used in strength and consolidation tests, example of which are the tube sample and the chunk sample. So for the soil exploration and methods, what is subsoil exploration? It is the process of determining the layers of soil strata and physical properties needed to assess the soil for the proposed structure. The purposes are: first, selection of the type and depth of structural foundation. Next, assessment of the load-bearing capacity of the foundation. Third, estimation of settlement of the foundation or structure. Fourth, the determination of potential foundation problems. Fifth, establishment and locating the groundwater table. Next, we have the prediction of lateral earth pressure. And last is the formation of construction methods for changing subsoil conditions. The scope of soil investigation are: first, the type, size, and importance of the structure. Second, the client and the engineer's familiarity with the soil at the site. And last is the local building codes. So for the phases of soil investigation, we have phase 1, or the compilation of existing information regarding the structure. So it includes gathering information such as the type of structure to be constructed and its future use, the requirements of local building codes, and the column and load-bearing wall loads. For phase 2, we have now the collection of existing information for the subsoil condition. Existing information regarding the subsoil conditions at the site under consideration are: we have now the site plan, previous geotechnical report, topographic maps, air photographs, geologic maps, hydrological information, existing infrastructure, and the manuals. For phase 3, we have now the reconnaissance of a proposed construction site. So it is the visual inspection of the site and the surrounding area, so which includes the type of vegetation, proximity of natural drainage, adjacent land use, location of underground and overhead utilities, erosion features, cracks in the walls of nearby structure or structures may indicate settlement, and equipment storage areas or security. Next is phase 4, the detailed site investigation. So it consists making several test borings at the site and collecting disturbed and undisturbed soil samples from various depths for visual observation and for laboratory tests. So it is as well the determination of the groundwater conditions, and it is to conduct in situ or on-site tests. And last phase is the soil exploration report. So it is the preparation now and for the planning and design of the respective persons. So for the soil exploration report, we have now the scope of investigation, the general description of the proposed structure for which the exploration has been conducted. So we have as well the geologic conditions of the site, the drainage facilities at the site, details of boring, description of subsoil conditions as determined from the soil and rock samples collected. We have groundwater table as observed from the boreholes, details of foundation recommendations and alternatives, any anticipated construction problems, and limitations of the investigation. So the following graphic representations also need to be attached to the soil exploration report. So we have first the site location map, next the location of borings with respect to the proposed structure, third is the boring logs. So these are sample of boring logs that presents the gathered information per specific depth of every 1.5 meter or 5 feet. So fourth is the laboratory test results, and last we have the other special presentations. So next is the sample geotechnical investigation report. So for the disclaimer, I do not own this report. So that is why some informations and some pages are not included due to data privacy. So, and the presentation may vary as long as the contents are complete. So first, we have the table of contents. So it presents already what is the overview of the following pages or the geotechnical investigation report. So next is the introduction, then followed by the various test procedures such as the field test and the laboratory tests. Next is the site description and the general findings and recommendations. And include as well slope stability analysis if needed. But if that is on a flat surface, then just consider or have to be in a written form that it is generally on a flat location. Okay, so next, the following are the NSCP requirements or the National Structural Code of the Philippines requirements. So foundation investigation shall be conducted and a professional report shall be submitted at each building site. So for structures that's two stories or higher, but actually for our case, sometimes it is about 3 stories or we have 2 stories and an attic with the same floor area with our respective stories or floors. So an exhaustive geotechnical study shall be performed to evaluate in situ or on-site soil parameters for foundation design and analysis. So all boreholes should be drilled to a depth of at least 5 meters into hard strata or until a suitable bearing layer is reached, unless specified by the consulting geotechnical engineer. And for buildings with basements, the depth of boring should extend to twice the least dimension of the structure's footprint, or that is 2B. Again, twice of the least dimension, that is the width, added to the depth of the basement. So the table shown contains the minimum required number of boreholes per structure. Example, if we have a building with a floor area of about 100 square meters, then the number of boreholes will fall for the second row now. That is, we have a minimum required number of 2 boreholes. On the other hand, the depth of boring for a building with a width of 30 meters or 100 feet will be approximately the following, according to sowers and sowers. So we have now for our first column the number of stories or the number of floors, while for the second column we have now the boring depth. So with the respective in metric or in meters, and in English we have now for feet. So for hospitals and office buildings, according to sowers and sowers, for light steel or narrow concrete buildings, we have now D sub B or the depth of boring all over S raised to 0.7, or that is for S the number of stories is equal to A. So for A, we have now 3 if D sub B is in meters, while that is a value of 10 if D sub B is in feet. Therefore, to determine this D sub B, it is now equal to A times our capital S raised to 0.7. On the other hand, for heavy steel or wide concrete buildings, our D sub B over S raised to 0.7 is equal to B. So just replace B with 6 if D sub B is in meters and 20 if D sub B is in feet. And the range of spacing of boreholes are shown in the table. So we have the different types of projects and the corresponding spacings based on the specification or the units of or system of units that is either in metric or in English. Okay, so that's it for the review of the fundamental concepts of the geotechnical engineering. Take care and God bless.